Okay, good day, everybody, and thanks for attending this talk. It's the fifth talk of the Full Displacement Hazard thematic laboratory, and today we have Octavi Goméz Novell as a speaker. He's now a researcher at the Instituto Geológico y Minero de España, and he got his PhD from the University of Barcelona, and his works focuses mainly on characterizing active fault through geologic mapping, paleoseismology, and modeling. He worked in Spain, in Italy, and I think maybe somewhere else. And today he will present one of his last work revolving around modeling. And the title of the presentation is Fault Surface Rupture Probabilities Derived from an Earthquake Cycle Simulator. So, Octavi, now the floor is yours, and as usual, at the end, there will be room for questions.
Okay, thank you, Francesca. I'm going to share my screen. Everything is correct, right? Do you see it correctly?
Yes, perfect. Yeah.
Okay, that's great. I'm trying to move this away. Okay. Okay, so thank you very much for inviting me to do this talk. Today I'm going to present you a work that we've been recently doing, and is mainly a work in progress, but we are getting there. And it's about is a work that is focused in investigating the probability of surface rupture. In this case, derived fully from an earthquake cycle simulator. And this work, of course, I'm presenting it, but all these people listed in here below are involved in this. So, of course, they are also part of this. And if you have any questions that I'm not able to respond, you can also ask these people as well. Okay. So yeah, very fast, because most people here connected is familiar with this, but this work is mainly focused on the phenomena of surface rupturing that, as you know, is one of the hazards or one of the worries also when there is large earthquakes. No, you can see here in this image, for instance, of the Kaikoura earthquake in New Zealand, that surface rupturing is really can be really a problem. No, and this is because surface rupturing basically affects infrastructure, society, and also can trigger other geohazards, like this paradigmatic case of the Papatea Fault in New Zealand that triggered a river avulsion. No, so one of the main questions in these kinds of works is basically how or can we forecast and characterize surface fault ruptures? No, this has been the main topic of the fault displacement hazard studies, and the main question is how to do it. No. So basically, this how goes through basically characterizing first the activity level of the faults at study, also the complexity of the ruptures that can happen during large earthquakes, and especially, and of course, when and where these ruptures can happen. And this is a question we tend to answer through forecasting. So basically, the fault displacement hazard world, let's say, has been relying a lot on empirical data. No, for instance, here I have some examples of this work by Sarmiento et al., in which they collect data from a lot of worldwide earthquakes that have ruptured the surface, and basically these works rely on building large data sets, or as large as possible data sets, to have the most data as possible for earthquakes. No? And this implies a lot of work of collecting data, both in the field and also remotely, etc., no? To build all these databases. And all of this is done to then derive the statistics that help us in fault displacement hazard, both in quantifying the likelihood of surface rupture, and this is done depending on the tectonic setting, the type of fault, etc., and also the probability of fault displacement hazard analysis. So based on these likelihoods, building hazard analysis, both fault specific and also along strike, like this image that you can see here, for instance, by Testa et al. in Italy. But as you all know, because most of you work in these topics, empirical data has many problems, and it's basically related on the completeness and the amount of data that we have. No, usually the data on earthquakes, and especially earthquakes rupturing the surface, is that we have scarce data, and especially scarce quality data. And this is difficult for us to quantify the long term, and especially to quantify how earthquakes happen and rupture the surface over the seismic cycle. No? So with this problematic in mind, what we did is basically, sorry, okay. So we basically, we thought, okay, let's try to employ an earthquake cycle simulator to try to overcome, or at least understand how this lack of data is impacting us, no? To overcome these empirical limitations. So in this study, basically what we did is we employed an earthquake cycle simulator. I will explain later how this simulator works really fast, but it's basically the RSQ sim. And we did these simulators have the advantage that for once they allow us to complete the earthquake catalog by simulating cycles, so several seismic cycles, so several sequences of earthquakes in large earthquake catalogs, and also they allow us to have information, so a full view of the ruptures that happen in a fault or in a fault system. No? And in this study, especially, we have been focusing, we are focused, or we are interested on characterizing how the geometry of the fault, and especially the roughness, or better said, the sinuosity of the fault, is impacting on the probabilities of surface rupture. So in this study, we started small, no? Let's say what we selected is a very specific case study. In this case, it's the Montevetore fault in central Italy, which is the responsible for the 2016 central Italy earthquake sequences. And we selected this fault because it's a fault that we have, and the fault trace is known. We also have several geological data that we can confront our models with, but the, let's say, interesting thing is that we don't know exactly the depth geometry of this fault. So this allows us to explore this geometry and see how this impacts the surface rupture probabilities, and also how they compare to the observation data. So I'm going to go very fast to the RSQ Sim simulator, which is the tool we have relied on to do the modeling. So basically, RSQ Sim is a computer code that works by simulating several seismic cycles based on the rate and stay law that was developed by Dieterich in 1979, but has been evolving a lot since there. And you can see here the equation of the basic equation of the rate and state that RSQ Sim employs. I'm not going to go a lot into detail in this, but these simulators have quite a lot of parameters that we have been working on a lot to try to match, or to obtain the best parameters. So in this study, what we did first is we did a parameter selection following benchmarking tests to select the best input parameters, especially for the normal and shear stresses, the initial stresses that you impose in the models, and also the rate and state coefficients that define the behavior, the seismic or aseismic behavior of the fault. So we have selected these parameters in an in-depth, let's say, more independent way. This benchmarking method is a method we developed basically that confronts the simulated catalogs with empirical observations, for instance, the empirical loss or the shape of the magnitude frequency distribution, to end up selecting which is the best one. So in this case, we end up selecting these parameters of the normal shear stress and also AMB, the one selected in green. And there's also many other parameters, and in this case, we use the defaults by RSQ Sim, which is more or less the standard practice for now. Okay, so now I'm going to go to the methods. No, so the center of this study is basically to explore the geometry of the fault. So the geometric exploration for the fault is divided into two parts. For one is we have explored how the fault, so this fault is divided into several segments, as I showed you in the previous map. So the first step is to develop models that are defined by how these segments connect at depth. No, so we have a first level in which all the segments are disconnected from top to the bottom of the seismogenic thickness. The second one, we consider that these models are connected at depth with a constant dip, and the second one, which is connected geometry as well, but with a variable dip, so a least strict geometry. This is for the depth connectivity, and we also developed another level or layer, which is the trace sinuosity. No, so for these three connectivity models, we developed 4 other types of models, no, which are defined by which is the geometry at the surface trace and the trace at the bottom of the seismogenic depth. So we have the first level, which is basically a linear trace at the surface and a linear trace at the bottom of the seismogenic depth. Then we have a trace linear, which is at the surface we have the geological trace, the one that is mapped, and at the bottom we have a linear trace. The next level is the geological trace at the surface and a smooth trace at the base. And finally, the most complex one is basically we have the same trace at surface and the same trace at the bottom of the seismogenic thickness. So this way we have like an exploration matrix of several geometries to test the impact. Yeah, sorry, just to clarify, this is basically the fault plane. There is a lateral view with an angle, not just in case it's not that clear. I can show you later if you want in 3D. Another important part of building the model is prescribing the slip rate. Sorry, these models work by basically backslip loading. So basically, you are prescribing the slip rate into each element of the fault. And in this case, what we did is we tried to impose a slip rate distribution that is not uniform throughout the whole fault plane. And this is done because these types of modeling, especially RSQSIM, if you provide a uniform slip rate distribution throughout the whole fault plane, it tends to develop fault stress singularities at the fault edges that tend to nucleate earthquakes in a non-realistic way, let's say. No, you would have a lot of epicenters nucleated at the borders. It's basically a border effect. So in this case, following the procedure from several other studies, what we did is we tried to develop a distribution like this, no? That is that you have the higher slip rate near the bottom of the seismogenic depth, which is a quite realistic assumption, but trying to first preserve the slip rate at the surface that matches the one that is observed in geology, so around 1 millimeter per year, and also that the average slip rate of the whole fault, so all the average slip rate of all the fault elements, it matches also the geological one. I say fault elements because these models work with discretized fault planes. So basically, the fault surfaces are discretized into small triangles that are the ones that allow for the model to work. And then just to go quite fast in this, the next step is to run and to run the models and do a catalog check. So basically what we do is run models for 100,000 year long. So it's simulated catalogs of 100,000 years. But what we do is we basically discard the first 50,000 years, so half of the catalog, because in this way we allow for the stresses to evolve enough in the model so that they are more far away from the initial conditions. And this way is more reliable. And then once we have these models, what we do first is we check that the models more or less fall within the uncertainty of the empirical relations. You can see here, for instance, 2 example models. And each point you can see is one of the earthquakes from the catalog. This is the relationship between rupture area and moment magnitude. And you can see, for instance, that more or less all the catalogs fall within the empirical relationship, in this case by Leonard to 2010. And then the step that concerns us in this in this laboratory is basically estimate the probability of primary surface rupture. And this, of course, is on the principal fault, because in this study we have not modeled secondary faulting or distributed faulting, just on the principal fault. because we wanted to test if this approach works to do this kind of study. So basically what we did is we compute first the likelihood of surface rupture, basically in two ways. No, for once in the whole fault, so basically dividing the number of events that reach the surface per each magnitude bin versus the number of events total of that magnitude, because we can have events that do not rupture the surface in the model as well. And we do the same along strike. No, in this case, magnitudes equal or above a certain magnitude threshold. And you can see here, for instance, in this plot, that we have for each fault element at the surface, or each fault element in the model, the number of events that reach the surface for a set magnitude versus the total event count of that magnitude, which here for simplicity is represented as this red line. And then with this information, what we compute is the conditional probability of surface rupture. Basically, we fit a logistic regression following the equation that most of you may know by Young et al. And then the last step that we do is we want to see how good our models at predicting or trying to agree with observation. So basically, we compare the surface slip distribution of the models with the coseismic slip of the 2016 earthquake, and also with the cumulative surface slip in the area. So the measurements, the geological measurements, basically. So in this presentation, I'm going to focus, especially as I said, with the impact of geometric connection of the fault, and also the sinuosity of the trace of or the fault trace at top and bottom of the seismogenic depth into the earthquake catalogs. So the first step here is to try to observe the magnitude frequency distributions. So the whole catalog, the Gutenberg-Richter distribution of the catalogs, depending on the connectivity model and also the sinuosity of the fault. So on the left, you have the model that is disconnected. On the center, you have the model that is connected with constant dip, and on the right, sorry, they're connected with variable dip. And in each plot, you have the different Gutenberg-Richter distributions for each one of the sinuosity levels that we consider. So what we can see, first of all, is that the disconnected model tends to converge a lot. No, you can see that the Gutenberg-Richter distributions are very similar, regardless of the sinuosity that we consider in the model. And this is a thing that is not observed for the other models, the ones that connect at depth. We can see that the models that don't consider sinuosity, so that basically are the fault traces at top and bottom of the seismogenic depth are straight lines. You can see that these models tend to have a very characteristic magnitude frequency distribution with a high deficit of moderate magnitude events. And this is the thing that disappears as we increase the sinuosity. We can see this for both models of constant dip and variable dip, so a least strict geometry. Then what we did is we analyzed also the maximum magnitude of this catalog. So what we did is basically we perform moving, we do a moving time window of 18,000 years, sorry, along the 50-year earthquake catalog. This 18,000 years is the time period that is the geological observation of the fault in the Apennines, more or less. So what we do basically is we compute the probability density functions of the maximum magnitudes along the whole catalog by moving this time window. And what we observe is that usually the connected models tend to give maximum magnitudes that are much larger than the disconnected model. You can see, for instance, we confronted, we have the same structure here than the previous slide, the disconnected model on the left, the variable dip on the right, and the connected with constant dip in the middle. You can see, for instance, that the disconnected model, the maximum magnitude of any of the models does not reach the 2016 magnitude earthquake, the 6.5. So that is interesting. In the connected with constant dip, we observe that some of the catalogs, some of the models reach this magnitude while some of the others don't, and we see that the sinuosity tends to decrease the maximum magnitude of the catalogs. And instead, in the connected model with variable dip, so the least strict geometry, we see that all the catalogs, so all the models match or predict at less the magnitude of 6.5 that was observed in 2016. Okay, so now from now on, the analysis that I'm going to show you are basically centered on the n members of each one of the geometry. So basically, I'm going to focus on the disconnected model, the linear, so the most simple one and the most complex one in terms of sinuosity, and the same with the Lie geometry, just for simplicity. So one thing that we were interested in, because it's one of the controlling parameters in the probability of surface rupture, is the hypocentral depth distribution. So in the disconnected model, so model that does not connect at depth, we observed that the peak of the hypocentral distribution is located basically at the bottom of the seismogenic depth, between 8 and 10 kilometers, around 9 kilometers depth. And we observed that this is quite controlled by the distribution of slip rate that we have imposed in our model. No? So we have more events where the slip rate is higher, because in that observational time period, we have a higher number of events. And we can see that in this case, increasing the sinuosity does not change too much this distribution of hypocenter depths. If we move to the connected geometry, in this case, we have the Lie geometry here. Sorry, this is a typo. This should be with variable deep, sorry. But what we observe here is that even though we impose the same slip rate profile, as you can see here, the maximum, the peak of the hypocenter distribution is not located where the maximum slip rate is, but instead is located where the faults join that depth. No? So we have a geometric control here on the distribution of the hypocenters. What's interesting to see here also is that the model with higher sinuosity, so in this case sinuosity, tends to nucleate a bit more earthquakes towards shallower parts. So in this case, the sinuosity of the fault tends to act as asperity in some of the regions. And here, quite very fast, so we have an idea. The hypocenter HDD relation of the hypocenters are more or less around those that are observed in earthquakes in Italy. We have here, this is a figure by Lisa Mamarella. So you can see that for Italy, the red straight line is the HDD distribution of the earthquake. So in our models, in both models, in the connected and disconnected, the peak of the hypocenter depths fall within the maximum of the distribution in central Italy. So it's a nice result. And then we move to results of probability of surface rupture. So first of all, what I wanted to show you is that the probability of surface rupture is basically independent of the total earthquake rate for a given observational time. So here you have two examples of two models, and we can see on the y-axis the probability of surface rupture, and on the x-axis the magnitude. And we have done this analysis, so we have performed the probability of surface rupture per magnitude bin by moving time windows, and we can observe that for different time windows the earthquake rate changes. But the probability of surface rupture is more or less independent. You can see that, for instance, in some cases, in one magnitude bin, for instance, this one, the earthquake rate is lower. So the lower earthquake rate is at the bottom, and in this case, the lower earthquake rate is at the top. So the probability is higher. No, so they are not correlated. So this means that the observations of probability of surface rupture can be used or extrapolated to regimes so not regimes, but are independent of the slip rate of the fault and therefore the earthquake rate. So, and then we use all this data for all the cases to compute the probabilities of surface rupture, so the regressions. And here I have here I put you an example. So just for clarity, on here we have also the same models. No, linear is no sinuosity. Trace linear is a bit of sinuosity. No, so the sinuosity increases. Let's say on the bottom graphs, and the same for the left. So the most complex one is trace. The less complex one is linear. So basically, what we can see is that in general, the regressions are more or less similar, regardless of the geometry that we use. No. with this, we have some comments on that as well. We can see also that the shape is more or less consistent with numerical solutions. No? So in this case, what we do is we confront all the regressions for the different connectivity models, and we confront them with empirical regressions, which are, you can see the references here, basically Youngs et al. 2003 and Pizza et al. 2023. And we also compare with the regressions from a numerical approach by Lisa Mamarella et al., which is the green line here. No? We can see that the shape of our distributions, so our regression, sorry, is more consistent with the numerical approaches than the empirical ones. This makes sense because the empirical approach by Mamarella et al. Is more fault specific than the empirical regressions. No, the approach by Mamarella et al. Is basically specifically for a given number of the same seismogenic depth. No, so one model is for one seismogenic depth, which is more similar to the configuration of our models than the empirical relations that in fact they tend to mix different types of faults with not types of faults, but different faults with different seismogenic depths, which tend to smooth out or flatten out the distribution. And what is important here to see is what I just said, that in general, the models without sinuosity are slightly more in agreement as well with the numerical regression. And this also makes sense because these numerical regressions do not consider sinuosity in the faults. It's basically using a planar geometries. Then for this, what we also did is we computed the differences in probability. So the differences between the different regressions, and in this case we took the central model that connected with constant dip as the reference, and we computed the differences for the disconnected geometry and for the Listric one for each one of the sinuosity models. So what we observe from scratch is that the probability differences are in general quite small from model to model. You can see that the differences are basically 20%. So 0.2 probability. So it's not a very large number. And what we observe as well is that the models without sinuosity, in this case the linear, are more sensitive to the geometric assumptions than those with sinuosity. We observe this because the range of probability differences is larger in the model without sinuosity. But what is also interesting to see is that we do not observe in these differences, we do not observe a trend in the sinuosity nor in the type of connectivity model. We don't see that, for instance, increasing connectivity tends to give higher or lower probabilities. So what we conclude is that basically a sinuosity and geometric connectivity are not a good predictor or not predictor variables for the probability of surface rupture, but these geometries impact the probability of surface rupture, just that we cannot use them as predictor variables. Then what we also did is not just looking at the regressions, but also computing the probability of surface rupture along the trace. In this case, it's for magnitude equal or above magnitude 6. So here you can see a very small example or just a glimpse. You can see on the left the model without connectivity at depth, so disconnected model, and on the right the model with connectivity, the Listric geometry. And in this case, you can see that there is a very clear impact on the distribution, the spatial distribution of the probability of surface rupture, controlled by the connectivity at depth. No, the disconnected model, you can see a very large impact of the segmentation, and on the right, which is the connected model, you don't see this impact as much in the segmentation. I will show you a bit more about that. This is just two examples, but we also, in this case, plotted the probabilities of surface rupture along strike for all the models that we perform. We have the disconnected geometries here, the connected with constant dip, and the connected with variable dip. And from top to bottom, we have increasing sinuosity. So as I said, the spatial probability of surface rupture is basically controlled by the depth connectivity of the models. And you can see that in the disconnected case, we have a high control of the segmentation. So we have a segment that consistently, in this case, returns probabilities that are very close to 0. And this is because this segment might act as a as a stop for rupture propagation. That's why also in this model we have lower maximum magnitudes. But for the connected models in general, this implies, so higher connectivity implies higher probability of surface rupture and a higher concentration of the probability towards the central parts of the fault, mimicking also the slip rate distribution that we observe at the surface, which we do not observe for the disconnected. And then, okay, what we try to do is see how good our models at trying to predict the observations of geology. So how good they are, no? So basically what we did, as I said at the beginning, we compared our models with the distribution of the 2016 earthquake, the magnitude 6.5, and also the cumulative slip along fault for the last 18,000 years, so post last glacial maximum. So I will start with the coseismic slip. So here you can see as well a matrix of plots. On the left, you have the disconnected geometries with no sinuosity and maximum sinuosity, and on the right, the listric geometry, the connected at depth with no sinuosity and maximum sinuosity. So basically in this, for the coseismic slip, what we can observe, so again, sorry, here what we did is plot the slip distributions at surface for events around the magnitude of the 2016 earthquake, magnitude between 6.4 and 6.5, which are the red lines. These are all the earthquakes of that magnitude in our catalog, and the black line is the coseismic distribution recorded at the surface. And for the disconnected model, because we don't have events of that magnitude in the catalog, we did it with the maximum magnitude of the catalog. So in this case, what we observe is that the parameter that tends to fit better, so tends to give a better fit to the models, is increasing the sinuosity. We can see that the models without sinuosity tend to give displacements at surface much that are above, more or less, the distribution observed in the 2016 earthquake. What we also observe consistently is that in the southern part of the fault, so it is the Monte Vettore area right here, we are very off of that area. But this area, this is a bit of there's a bit of debate because it's the southern tip of the fault, and we might have other structures at play here that might be contributing also to sleep and we are not including in our modeling. But I'm happy to discuss because this is really this part we are really thinking about it. And the second part is trying to compare this instead of the coseismic slip with the cumulative slip for the past 18,000 years. Here again, we have in red the simulated cumulative slip for time windows of 18,000 years along the catalog. And on black, we have the cumulative slip registered at surface, or measured at surface for the same end model, so disconnected and listric. And in this case, what we see is that the models that are disconnected tend to be a bit higher, or so the difference with the observed cumulative slip is quite higher with respect to the ones that consider a connectivity at depth, in this case, the listric, no? And you can see also that the shape of the distribution of cumulative slip is, the trend can be comparable, except again for the Monte Vettore region at the southern part. And we insist here that maybe there are other structures at play here at the tip of the fault, or something that we are not modeling that might be affecting this. Of course, we are not considering erosion as well. So that might be why also we are quite off. So there are some implications on that I will discuss later. So just for discussion, what we try to do is a matrix to observe what parameters impact and how they impact the probabilities of surface rupture and the different statistics of the catalogs depending on the model. But what we can see is that the fault geometric characteristics greatly impact the simulated catalogs and also the surface rupture probabilities. As we have seen, the depth on the side of the depth connectivity, basically increasing connectivity increases the maximum magnitude of the catalogs. It also impacts the probability of surface rupture, although we cannot see a trend of increasing or decreasing the probability, but we have seen that it increases the spatial distribution. So the probabilities in the spatial distribution of the probability of surface rupture. And we have seen that increasing connectivity tends to fit better the observations, in this case, the long term, so the cumulative slip. On the other side, we have the roughness or the sinuosity of the fault, which basically tends to lower the maximum magnitudes in the catalogs. It also impacts the probability of surface rupture in terms of the regressions, although not in a clear trend, and it tends also to decrease a bit the probability of the surface rupture in spatial terms, and also increases the fit to the observations, especially for the leucoseismic distributions. So just as a few conclusions, so basically the most geologically realistic geometry is the one that best mimics the observations, both coseismic and the cumulative, and also the maximum magnitude observation is the one that fits better the fact that we had an earthquake of magnitude 6.5. Also, that geometry impacts the spatial probabilities, but not as much in terms of the regression. So we do not see a very clear change in the regressions. We are aware also that we have quite large deviations from the observations that might result from a series of very oversimplified modeling choices, including stress and the friction distributions of the RSQC model, because in this case we used very uniform parameters of the normal stress, for instance, and also the A and B of the rate and state. We are also not including erosion and, of course, other structures that might be interacting with the fault that we are modeling and could be altering as well the observations that we take out from these models. And also we observe that our models deviate as well from empirical regressions, but are closer to fault-specific regressions that are based on numerical approaches, which are more closer to the method that we are employing here. So just to conclude, we think that earthquake cycles have a high potential for probabilistic fault displacement hazard because they can help us to complete observations or to allow to simulate more earthquake catalogs, increasing the number of events or to do more robust statistics. Also because they allow us to do quite detailed spatial distributions of the probability, and also because they can work as a site-specific. So they can be used for site-specific purposes that maybe the empirical relationships sometimes cannot provide. But yeah, I'm done here, but I'm very happy to discuss. As I said, this is a work in progress, so any ideas or suggestions or critiques are welcome. So thank you.
Thank you, Octavi, for the very good talk. And now I'm opening the Q&A session. If anyone wants to unmute and pose question to Octavi. Okay, Paolo, you are the first.
Just to break the ice. Thank you, Octavi. Very nice talk. Very nice work. Promising work. If you could you go back to the slide with the probabilities of surface rupture, the one with the dots.
Yes.
So it seems that the probability is close to 1 for magnitude less than 6. Am I right? So it seems to increase the probability of surface rupture compared to existing models, for example.
Yeah. Exactly, yeah.
And for example, in the Mammarella et al. Model, you have mentioned and used it as a comparison.
Yeah.
You said that, okay, it is closer to my result because it is a numerical one. And in the Mammarella et al. Conclusion, there is one main parameter is two parameters are important. One is the thickness of the seismogenic layer. The second one is the depth of the fault, of course, because you may change the area of the rupture. Okay, so in your model, everything is fixed. So why it is so higher, the probability? Well,
Okay, yeah. So basically, what we observe, for instance, in this figure right here, is that we have two parameters that, in our idea, are impacting this. So for one is the hypocenter depth nucleation. So basically, in models with higher sinuosity, which in this figure, for instance, are the ones on the right. So the trace linear, trace smooth, trace are increasing sinuosity. In these models, we tend to have nucleations of larger magnitudes more to the shallower parts because sinuosity tends to act as asperities for the in the model, no? And you're nucleating events more towards the surface, so it's easier for these earthquakes to reach the surface, which does not happen in the linear model. That's why in the model without sinuosity, we fall within the estimate by Lisa, especially for the models with connectivity at depth.
So the depth of connection appears to be very important.
And also that the fixed seismogenic thickness. Yes. That's why the steepness of the seismogenic of the regressions is higher than the empirical. It's not a very big seismogenic thickness. It's 12 kilometers in this case. I haven't mentioned, sorry. So yeah.
Very interesting. So I hope to discuss more on several things, but
yeah, of course.
There are other questions.
Yeah, Alessandro, please.
Yeah, can you hear me?
Yeah, now yes.
Yeah, thank you, Octavi. Very interesting talk. And still talking about probability of primary surface rupture. And this curve that we are showing, I think, are extremely site specifics in terms of application for PFDH because they are generated with Monte Vettore fault parameters. So maybe this is also the reason why because they are so different from in particular for different from empirical regression because, for example, for magnitude 6, the difference is quite important because we go from 0.3 with the empirical regression to almost 1. And so this impact a lot PFDH hazard curve, for example. I don't have a question, just maybe an idea, maybe you're already working on it. What happens if you do this exercise with maybe 100 different fault configuration all around the world, and then try to average the 100 probability surface rupture? So maybe you will be much closer to the empirical observation or not.
Yeah, that's what we think. Yeah, of course, this study is not to provide the probability of surface rupture curves for the Monte Vettore. It's just to study the impact that the geometric parameters that we don't know impact on the on the surface rupture. We did just for one fault because we think that if we start with a lot of faults, it will be very difficult to assess what is the impact of geometry into these probabilities, because then you start having other fault interaction, other stuff that it's quite difficult. But of course, I think that including more faults, doing a larger data set will tend to fit better the empirical regressions. I think the flatter curves are due to this because you are putting faults with quite different characteristics. So yeah, I agree. This is the next step. But first, we wanted to understand. Yeah.
Thank you.
Thank you.
Okay, do we have other questions from people attending the talk?
Can I ask you a question, please?
Yeah, sure.
All right. Thank you very much for the talk.
Thank you.
I was wondering about the sleep models for these large earthquakes that we obtain from seismology or geodesy.
Yes.
So if you test these predictions for surface rupture versus the sleep models already published, in order to make a comparison which is against real data, I'm referring specifically to the geometry. I haven't seen for any major earthquake so far I know, no model has suggested holistic geometry. All the geometries are planar.
Yes.
Unless I miss a case or something like that, maybe 95% of all the cases I know are planar geometries from, let's say, 1-2 kilometers down to 12-13 kilometers.
Yes.
So have you considered that as a constraining factor in these models, in your models?
So you mean the source modeling of earthquakes? So the sleep, the inversion of the sources.
Yeah. You take even the Mount Ventura, for example, case or any major earthquakes. I've seen, especially strike-slip earthquakes, they don't seem to have any considerable elastic geometry at all, the fault planes.
Yeah. Yeah. So I guess in the source inversion, they are simplifying the geometries because we know the geometries at depth are not planar surfaces. So in this case, we're not working with that type of data. So yeah, the simulator returns a slip field in the fault plane, but the fault plane is that you pre-impose. But we think that more complex geometries tend to be more realistic. We can discuss how the complexity that we observe at surface translate at depth. No, that's why also we explore all these geometric end models. I'm not sure if I understood well your question. You're talking about comparing both, no? About
if you have, let's say, 150 well-constrained sleep models from seismology and geodesy.
Yes.
Right, and those earthquakes were either surface rupturing or not. For example, in Greece, there are now, for the Samos earthquake, magnitude 7, normal fault earthquake, there was no surface rupture, but there are already 3 or 4 different models published for the sleep pattern for this. So I'm really concerned about to compare the predictions and the observations.
Yeah, of course. So so the idea of these models is not to replicate exactly past events. So they are basically based. So they are designed to be to perform statistics on the surface rupture, not to replicate exactly the slip pattern of a single earthquake. Especially because these types of models are not. I don't think they reproduce well the process of rupture propagation. So they are not really designed to be confronted with single event data. They are just designed to do statistics, in my opinion. But of course, the statistics of the displacement along on the fault plane and on the surface, if you observe a large sample of earthquakes for a large time window, they are usually confrontable with those observed. But for a single earthquake, I don't think the comparison can be done that easily. I don't know if. Yeah, which is it's not what we are doing. Okay, we wanted to see if the Vitoria earthquake, the slip distribution falls within the cloud of events of similar magnitude in our model, but not if it matches exactly the slip of that particular earthquake. I don't know if I answered your question.
Okay, thanks for the try.
Thank you.
Thanks a lot. Okay.
Okay, is there anyone else who wants to ask Octavi easy or difficult maybe questions? So I have one about the long-term geological sleep rate. So maybe if you can go to the slide, it's easier for me to recall.
So towards the beginning, this one?
No, one towards the end,
Okay,
where you compare
cumulatives.
with okay.
Yeah.
So my question is about the fact that in your model you have more or less a kind of plateau, so everything looks quite regular, while in the actual case where we have a very high asymmetry. So how can you, which opinion or which hypothesis can you add to this point?
So I think there's several things here. For one is that in our model, we don't consider any kind of erosion of the fault scarp. So this might be one cause of why we are always more or less over the observed cumulative sleep, and we don't have this this variability. This is one. The other one is that for sure, even though we are trying to model the complexity of the fault trace as much as we can, we are still simplifying a lot. So we are sure that there are smaller scale, because you have to think that the patch that we're using is 300 meters long, which for this model is quite detailed, but in reality you have fault details that are of a smaller order. So this is also, I think this can also be contributing. And of course, simplifications in the model. Like the one of that comes to mind is the rate and state parameters, that we are considering them equal to for the whole fault, but of course these parameters change in the crust, especially at surface, and this also might be impacting how the sleep is translated at the surface. So yeah, basically I think it's a matter of simplicity. So the way we think we can do this is by comparing if the trend is more or less comparable or more or less follows a similar geometry, especially in the fault, in the segment limits, etc. More or less, we think we can accept in the southern part, which we are very off. But yeah, it's the tip of the fault, and we know that there are other structures there. So I don't know if I answered your question.
Yes.
Thanks.
Can I ask again about this point, but not this diagram, the previous one with the co-seismic one?
Yeah, this one. Maybe I do it a bit.
Okay, because you got some asymmetry to the south. Is it right?
This part?
Yeah, the red line is from the model, right?
Yes, yes.
So you got some asymmetric distribution.
Yeah.
But so the question is, why? Why your profile is asymmetric? But of course, we know that the co-seismic one is very asymmetric. But I don't get why the model should produce this kind of what's the controlling factor?
Yeah,
in your model.
One factor could be because in this area we have a bed. There is so it's a a fault segment limit. So in this area you might be nucleating some events that tend to give a higher slip in that specific region. And you observe this especially in the models with sinuosity. In this case, you have a fault band as well in the sinuous model. So maybe you are also nucleating in that asperity. So at the end, the sinuosity acts as asperity. So maybe there you are more favorable to nucleate earthquakes. That's why you obtain these maybe these asymmetry. And also you have to consider that in the models we impose the same type of sinuosity throughout the whole fault. But for instance, we see that on the models without sinuosity, the cumulative slip model is more closer to the observed one, while in the sinuous model to the north is more closer. So we could explore models with varying sinuosity. So you have less sinuosity on the south because we observe that it fits better, and more sinuosity to the north, where we see that it also fits better. So these are just extreme models that we explored that, of course, we could do many other models trying to match these observations. But as I said to Athanasios, using single events to try to match the model, I think it's not the best way to do it, because these models are not good at reproducing the exact propagation.
Yeah.
Of course, no model is reproduces the exact propagation, no? But this one's especially.
Thank you.
Thank you.
Okay, so if there are no other questions, I want to thank Octavi
Thank you.
for the good talk, and you will find it soon on YouTube. And we are also planning a new talk with Alessio Testa. The date will be announced quite soon, I think.
Perfect. Thank you so much, Francesca. Thank you all.
Thank you.